Usually I would like to thank the organizers, but I guess we invited ourselves. But thanks to IPAM for giving us this wonderful opportunities and for all the speakers for this nice workshop. So today I will talk a little bit about this so-called lifting of quantum Markov processes. So I guess everyone here knows what quantum Markov process is, but not necessarily knows what lifting is. I didn't mean lifting some heavy weights, even though we are trying to work hard, trying to understand what's going on. Okay, so this is a joint work with Bo Wen Li, who is now at City University of Hong Kong. Okay, so let me just motivate, and as some of the previous speakers have said, that we're all coming from different backgrounds. So my background is really like classical sampling, continuous sampling, and PDEs. So I'm thinking many of my perspectives are from that world. Okay, so we're kind of newcomer to the quantum sampling world. So I would like to start with this kind of well-known example of the lifting. Okay, so on the left here, okay, so this is a very simple random walk. So just imagine that you have a circle and with n nodes on the circle, and you have a particle that lives on the circle. And what it does is that at every time it flips a coin, and depending on whether it's head or tail, it goes to left or right, okay, with a high probability. This is probably one of the simplest examples that we teach in like undergraduate probability, and we know that, of course, this is ergodic, and the convergence to equilibrium measure. In this case, it will be just a uniform measure on these n nodes, so each with probability 1 of n. And we also know that the convergence of the time that it takes is roughly n squared, because this is so-called diffusive scaling, so that the random walk given time t, it covers the space with the square root of t. Okay, so that's why it's n squared of mixing time. Okay, on the right, maybe it's a less familiar example. Okay, so that this is a chain on 2 copies of this circle. Okay, so we have the upper one and the lower one. And you should really think of this as just the 2 copies of that, so that we should identify this upper and lower nodes with just like it is a 2 copy of the single node here. Okay, and now this chain, what it does on this one, on the 2 cycle, is the following. So on the upper cycle, what it does is just that it always moves counterclockwise, okay, with probability of 1 minus epsilon. And the epsilon probability will flip to the lower cycle. Okay? And then once it goes to the lower cycle, what it does is that it always moves clockwise. Okay? And of course, there was also a probability that's going up. So first thing to notice is that also this chain, as you can also easily imagine, that the invariant measure is also uniform, okay, on both cycles. And also, if we identify like these two, so that we think about this as extended variable, so that's just indicating whether it's on the upper level or lower level. If we marginalize that out, and it claps back to this original kind of invariant measure, right, because it's a uniform. Okay, and you can even verify that if you think about the following thing, right. So let's think about this epsilon instead of epsilon. Let's think about this flipping infinite fast. Okay, so instantaneously it equilibrates between the upper and lower level. And then what it does is very similar to this symmetric random walk, because with high probability, you will be on the upper level. You're going to this side, this way. With high probability, you're on the lower level, and then go this way, right? So that it's going to be collapsed back to this original random walk. Okay, is the example clear? Yes?
So if you identify pairs of nodes on the right, there's a chance that it stays at a given node, which is not a feature of the left. Am I understanding that correctly?
No, I'm not sure I get your question. So you identified these 2 nodes, and then there was a what?
So there's a chance that it flips up, say, from the lower ring to the upper ring.
Yes.
In this quotiented system, that would look like it.
No, in the quotient system, then you do not distinguish, right? So that you have a high probability of living up and living down. And then, depending on the probability, you just go to right or go to left. So that's why it's going back to our original chain. Is that clear? Okay. Yeah, thanks for clarifying. All right. So, I think the one nice thing that was observed back in 2000 by Chris Diaconis, Susan Holmes, and Rob Neal is that if you do this, okay, then the mixing time of this simple random walk, which is n squared, reduces to order n. Okay, and which is not too hard to understand in a way, because here there was no direction, right? So that so here there was no direction, so it's equal symmetric, so it's like a random walk. While here, if epsilon is small, and actually this result holds when epsilon is like order of 1 over n, when epsilon is small, then most of the time you're just going in one direction. So you're doing the ballistic. I mean, it's a transport phenomenon instead of a diffusive phenomenon. So this is also known as a diffusive to ballistic speedup. Okay, so you can prove this. I mean, which is not too hard. That the mixing time reduces. There was a quadratic speedup. Okay, and also even though that I'm showing here a very simple example of a very simple geometry, you can imagine that you can construct examples for more complicated stuff. So, and one paper that I went out is this one that actually constructed such a lifted random walk on a tree. Okay, so which is fairly non-trivial. All right, is it clear? Yes?
Could you just say so I think I understand, but could you just say, so when the lifted random walk, so it mixes faster, and what is the stationary distribution? Is it just uniform everywhere?
Yeah. For this particular construction, it's uniform everywhere.
Okay, so it reproduces exactly the stationary distribution of a original.
Right. So if you want to recover the original invariant measure, you just forget about label whether it's up or down. So which is that case. Okay. Any other questions? Yes.
How small do you need epsilon to get the speed up?
1 over n.
Okay.
I mean, constant times 1 over n.
Right.
All right. So I think, thanks for all the questions. So this, I guess opened up some questions. For example, whether you can do something even better, right? So then this is a square root of acceleration, then maybe you can accelerate even further, okay? And unfortunately, as I guess for quantum people, this is not too surprising. The quadratic speedup is the best you can do, also in this context, okay? So this was actually proved, even though the paper was published before, but then it was actually after the Diaconis paper. So what they proved, by Chen, Lovash, and Park, is that this quadratic speedup is the best possible if you do lifting, okay? So it doesn't, not just for this kind of lifting, but in general. And I'll come back to this later also. And yes?
So I guess to clarify the word lift, meaning
So you construct a Markov chain on an extended state space, such that if you marginalize out the extended state space, you come back, you collapse back to the original chain.
The same stationary distribution, like
yes.
the same?
Yeah, so collapse back to chain, so that in particular the stationary distribution is the same.
Is it just the target distribution is the same, or the entire process?
No, the entire process, of course, is not the same because the state space is not the same. Yeah. Okay. And also, one thing that I want to point out is that, so this chain on the right, if you look, this is not symmetric, okay? Because in particular, that on here, that is just going this way, counterclockwise, and here is clockwise, right? So this is not reversible using the physics language. And also, what's shown in that paper is that if you can do the same construction, you can think about a Markov chain on larger state space, but it's reversible, okay? And what they show is that if your lifted chain is reversible, then the acceleration is the most constant factor. There will be no square root of acceleration. Okay? So this is, yes?
So also here you lift one chain to two chain. Can you just keep going?
Oh yeah, in principle you can do the 3, 4, so on, but then I think this is what they show as a lower bound, so that you cannot do better. In terms of scaling. Okay, so maybe you can reduce the constant. Yes?
What do you mean by reversible? If the lifted chain is reversible?
The usual reversibility of Markov chains, so that if you're starting from an invariant measure, if you move forward, then that's the same as if you're starting from a measure, then move backward. Okay? All right, so as I said before, right, I'm not actually even from discrete classical sampling, I'm more from continuous classical sampling. Okay, so what does that mean? I think it was mentioned before, maybe in yesterday's talk about Langevin dynamics, so let me just write it down. It was never, for the conference I've been to, usually this appears in first day on first slide, but it's not the case here. So let me just remind you what is the so-called Langevin dynamics, which is actually the classical limit of Lindblad dynamics, if you want to connect this to. Okay, so this is Langevin dynamics. It describes the classical okay, so this is not a pointer, sorry. So it describes the, what happens here?
From the sidebar.
But
it's really a mouse.
How can I
need to click it and move it away?
Can I do that? I think maybe it's running out of power.
No.
It's not responding at all? Okay, maybe I will just do on the laptop. Oh yeah, now it works. Thanks. Yeah, somehow it works. Okay. So this is a classical dynamics. Okay. So or if you think about this as a Markov process, so it describes a particle with position x and velocity v or momentum v. Okay. And now if you look at the blue part, it just follows the usual Hamiltonian dynamics, so that the derivative of position is the velocity, and the derivative of velocity follows the Newton's second law, okay, which is given by potential. All right. And then we're thinking about this particle coupled with some environment, and the environment acting on a particle. There were two effects. One is the damping, so that there was a minus gamma v. Okay? And then there was the environment acting on the particle as some kind of noise, so it's Brownian motion. So the Brownian motion is also scaled by the square root to gamma. So this particular scaling is called fluctuation dissipation relation. Okay? And now if you have this, because this is a Markov process, we can describe this in a generator, just as what we are more familiar with as the Lindblad generator. Okay, so in this case, if we think about observable, so f is a function of the position and the momentum. If we think about how this observable evolves in time, or in the quantum language, this is the Heisenberg evolution. Okay, and it's given by a PDE, so it's given by an infinitesimal generator acting on the observable. Okay, and it can write down this generator or the PDE operator in this way. So you can separate the effect of this Hamiltonian part, the flow, okay, which is this what I call LA. Okay, so this is just Hamiltonian flow, and then there will be this red part, the orange part, which is like the interaction with the environment. So this encounters the fluctuation and the dissipation. Okay, so these are, if you like the PDE, so these are the terms that appears in the PDE. Okay, and now it's not so hard to verify that this dynamics or this generator corresponds to an invariant measure, which is given by this particular form, its density. So so we have seen many times in this conference that e to the minus beta h. So this is exactly that. Okay, so this is the classical Hamiltonian. So this is kinetic energy plus the potential energy. All right. And one structural information that I want to point out is that if you look at this generator carefully, and this is also the reason that I color code them using blue and red, is that the blue part is actually antisymmetric with respect to this invariant measure. So it's, you define a weighted product of the L2, okay? And the red part is symmetric. Okay? And this gamma is a damping parameter, which also appears in Professor Collins' talk, and there will be a tight connection between the two talks later on, you will see. Okay. Yes?
Yeah, I guess there's like, I guess Langevin just kind of get this, but is there some sense that this is unique? Like, is there some condition that if you write down this only gives you this specific?
So it's unique up to the sense that, so both of these things could vary a lot. So like, for example, how you interact with the environment gives you what kind of noises that you could have. But of course, if you do some central limit theorem, if you think about this particle is heavy and then the environment is a solution of very, very small particles and sending like n to infinity, then you can derive this. But it's not unique in the sense of this theorem by Lindblad. Because here it's much more specific, because this dissipation operator, this damping operator is a very particular form, right? It's not like, say, any jump operator or something like that. Okay. All right. So, usually this would be the background slide, and this one would be a new slide, but I think here we need to flip the order, so this is everyone knows what this is, okay? But also one thing, I want to point out is that here I'm also not considering a detail-balanced Lindbladian, because I think throughout the workshop, everyone is more or less considering detail-balanced one, but for me, everything is not detail-balanced, okay? So here, in particular, that we could have a general Hamiltonian here, or the Lamb shift, or things like that, so that this one is not detail-balanced, it's not symmetric, okay? And this is, of course, the jump operators and so on. And then let me also remark that I kind of neglect, there could be also a coherence term here, which if you want, for example, KMS detail-balanced, but I just neglect that, okay? So I write in this form. Okay, and also, it's very similar to the structural kind of observation that we had before. If we write this in terms of both of these super operators, the generators here, LA and LS, and the LA part, this Hamiltonian, the commutation with the Hamiltonian operator is antisymmetric, okay, and then the dissipation part is symmetric. And in particular, so when I say the symmetry, of course, we need to kind of define the inner product. What I'm going to use in this talk is the KMS inner product, okay, so which appears several times already. Okay, and in particular, if we assume these symmetries, that actually sigma is, you can verify that it's a stationary state. And I said that already that this generator is not detail balanced, and part of the purpose of this our work is try to understand how to understand the convergence of non-detail balanced Lindbladians. Okay, so now I'm quite grateful that Professor Cullen already gave a whole lecture about the Zeno limit, or in our language, the overdamped limit, so that I can just recall what Professor Cullen told us. Okay, so now just observe that, as we already see, in both classical and quantum version of these dynamics, okay, I forgot to mention that, of course, if you take a semi-classical parameter goes to 0, then we recover the Langevin dynamics from Lindblad, so that, so these are actually very tightly connected. So there's essentially the same physics to some extent. All right, so you can write these dynamics as observables that evolve in time as a generator that splits into two parts. One is symmetric and one is antisymmetric and one is symmetric. Okay, and we're thinking in the overdamped limit, we're thinking about a regime when the damping is very, very large. Okay, so the gamma goes to infinity, a strong damping regime. Okay, so now, if you just kind of thinking about some like asymptotic analysis when this is a large parameter or 1 over gamma is a small parameter, and it's very natural to do a series expansion, right? So that you just write down the form of asymptotic expansion, the leading order terms, the next order contribution, and so on and so forth. And you plug that into the equation, and you try to match the orders, and you get order by order some equations for these terms that appears in the asymptotic expansion. Okay, so now the leading order says that the observable, right? So if you have the symmetrical part of generator acting on observable is equal to 0. So this is what the leading order equation tells you. Okay? So which means that, of course, the observable is in the kernel space of the symmetrical part of the generator. All right? Or in other words, if you define, because we have inner product, and KMS inner product, so we can define the orthogonal projection, which means that if you apply the orthogonal projection on the observable, you get itself. So it lives in the kernel of the symmetrical part of the generator. All right. And now if we put that, if we put this thing into a next order equation, and then project both sides on the kernel of LS, and you realize that the evolution of the A0 in the kernel follows this equation. Right? So the notation is a little bit different, but this is exactly what Professor Cullen told us. This is the, I think, LP that in his notation. Okay, all right. So now, in particular, on the leading order, if you think about the evolution of the observable, it's actually just given by this effective dynamics, okay, which only lives in the kernel of LS. Of course, to make this interesting, right, non-trivial, you need the kernel to be larger than 1 dimension. Otherwise, this is just, it's a trivial number, okay. And also, the observation is that actually for many interesting dynamics, especially Langevin, and also for many Lindbladian dynamics, what we have is that actually this leading order effect is 0. Okay? So this, if you projected the action of the Hamiltonian part on the symmetric space, symmetric kernel space, and what you get is there was no evolution at all. Okay? So then, then in this case, of course, the effective dynamics just tells us that on the leading order, the things are not moving. Okay, so which is not, of course, interesting. If we want to see some interesting non-trivial dynamics, this tells us that we should look at a longer time scale. Okay, so that this is the linear order time scale, so it's order 1t, for the original equation. And so we have to look at longer time scale so that we need to do time rescaling. Okay, in other words, so we need to change time to time t over gamma so that here, if the original time is gamma, in the new equation, the t is order 1. Okay? So this way that we look at longer time scale. And if you just redo the same thing, with a rescale dynamics, okay, so you do the same thing of the matched order asymptotics, which I'm not going into the details, but you see that one thing in particular is that for the solvability of the next order correction, and that actually corresponds to this condition that this projection of LA and the projection is equal to 0. Okay, and if we're in that regime, and what you recover is this kind of effective dynamics on the second order. Okay, so that you see that the observable, it will evolve in time according to this generator. Okay, the form, looks a bit complicated, but essentially the features is that you see that there is this pseudo inverse of the symmetrical part of the generator there. And in particular, if you think about it, you have a gap, so this one is bounded from above, Okay, but if there was no, of course we have a kernel, so so that's the pseudo inverse is well defined. But if there was no gap, then there was some bit technical issues. But for example, you can see what Professor Collins did in the paper. Okay, and then now these two parts are coming from from these LAs. Okay, so that you see that there were these antisymmetrical part of the generator here. So this is kind of like a square. All right, and then, what we have done here, we can make this rigorous, is that on the leading order, the overdamped dynamic in the case of very strong damping, this structural assumption is valid, then the effective dynamics is given this effective generator. Okay, so now the reason that I'm repeating this story that already appeared in previous talks is the following. Okay, so if we apply this framework, this is general. This really does not depend on what kind of generator you have here. As long as you have this time scale separation, you can do this exercise. Okay, and if you apply this to the Langevin dynamics that we just discussed, okay, so that you call that we have some Hamiltonian part and some damping parameter times the fluctuation dissipation part. And if you derive the overdamped limit of that equation, you get the so-called Smoluchowski equation. Okay. So, which there has many names. So, sometimes actually people just call this Langevin equation, but that's not correct. Okay, so this is overdamped Langevin equation. All right. So you see that here this equation is only equation in the position. Right. There is no momentum variable. So that previously we have both x and v, and then you in the limit that gamma goes to infinity, so inertia dominates. So that the v would essentially just equilibrate very fast. Okay, because the gamma is very large. Okay, so you only need to track the position degree of freedom. All right, and also as we have seen already, so in the quantum setting, this name, in the classical world, this is usually called overdamped limit. In the quantum world, it's usually called Zeno limit, which we have already seen these papers already mentioned by Professor Collins yesterday. Okay, so now the reason that I'm talking about these overdamped limit is that remember that we started with this example of lifted Markov chain. Right? So that the idea is that you extend the phase space and you define a process on that enlarged state space, and so that the enlarged state space will class back to original chain and hopefully you get some acceleration. And now if you compare these two dynamics on the classical world, right? And you see that's very similar in the sense, so that here this is only dynamics on the state space of the position variable, while this dynamics is actually both in position and the momentum. Okay? And you can also check that the invariant measure, so this one is actually, if you marginalize out the velocity degree of freedom, you get the invariant measure of this chain, of this process. Okay. And now, if we just think about the opposite direction of the thinking overdamped limit, right? So sending gamma to infinity. So let's say we're not trying to send gamma to the infinity, okay? And we just want to use this dynamics as some Markov process on the extended phase space, okay? So you can think of this Langevin dynamics as a lifting of the overdamped dynamics. All right? So in particular, if you want to sample, the classical sample, right, continuous sample, of a Gibbs measure corresponding to this potential, so you want to sample e to the minus u, what you can do is that you can run this extended process, and in the end of the day, you marginalize out the velocity degree of freedom, and you recover the invariant measure of this one. Okay. All right. So now setting up this as kind of, and this is also kind of lifting, right? At least here is the understanding. So this is very analogous to a discrete case where we can look at these lifted Markov chains. A natural question arises, of course, whether we also have a quadratic speedup or we have some speedup here. Okay, so in the sense that the convergence to equilibrium of this dynamics, and we want to compare with the convergence to equilibrium of this dynamics. And now let me remind you that, of course, you get this overdamped dynamics when gamma goes to infinity. So in other words, if you want to achieve any kind of acceleration, you are not going to work in the regime near the Zeno limit or near the overdamped limit, so that gamma would be something that is order 1.
Can I ask a high-level question? Why quadratic speedup? Because quantumly, people can vaguely attribute it to the...
Yeah, I'll explain that later. So we will actually have a theorem to explain why there was a quadratic speedup area, at least in this setting. All right. Okay, so is the motivation clear, at least, so that we want to see that whether this accelerated, whether there was acceleration, okay? So, of course, before acceleration, so I think many of the audience may not have seen Smoluchowski equation before. So let's actually just recall what the convergence we have here. This is actually a reversible process, which is probably not so clear from the first sight, okay? But it is, and with respect to the weighted inner product, okay? So, and now, as I said, we're kind of more used to thinking about things in terms of PDEs, and so that let's write down the PDE. And now if you kind of, so I think it appears already that we can look at the generator because it's reversible. We can think about its spectrum, okay? So if we assume a spectral gap, then you have exponential convergence with the rate given by the spectral gap, okay? So now just translating language to PDE, this means that you assume some functional inequality, which is known as the Poincare inequality. Okay, so this is really the spectral gap written in the sky, so because this one is the Dirichlet form of the generator. Okay, and if you assume that there is a spectral gap, okay, because we know, for this dynamics, the kernel is just a constant function, all right, because we're in the Heisenberg picture. All right, and so now, if you assume that, if you have a spectral gap, then you have in the L2 norm the exponential convergence with the rate just given by the spectral gap. Okay, so this is just a classical fact that everyone knows, but just written in the PD language. Okay, so we have seen that this chain, okay, so this process, this overdamped process, converges. The convergence rate is related with the Poincare inequality. Okay, given some assumptions of the potential U, you can try to establish what the Poincare constant is, but let me not go into the discussion of these things here. Let's just assume that you have some Poincare inequality, and which is given by M. All right, so now what, as you can see, so essentially the above, the key of this convergence is essentially just spectral gap. And now in this language, right, so that you can write it as a Dirichlet form. So, we can also understand it, using a slightly different language, is the coercivity. It just means that the Dirichlet form is bounded from below. Okay, so this is just another way of saying that there is a spectral gap. Okay, so now the first thing I guess one would do is that, okay, so if we have this non-reversible process, okay, so this original Langevin, the difference compared with the previous one is that we have two parts, remember, there is an antisymmetric part and plus gamma plus the times the symmetric part. Let's do the same exercise again, right? So let's just try to put in the Dirichlet form on the right-hand side and see if it's control the L2 norm. Okay, if it does that, it means that it has a spectral gap, and then we can do the same exercise. And unfortunately, because of this antisymmetry, okay, so this is a feature of the, I guess this is also the reason that why many works in reversible cases, because reversible cases are significantly easier. Okay, so because of this non-reversibility, if you do the same calculation, you plug it in, okay? This should be S. Okay, so the only thing left here is the dissipation part, is the LS. Okay, the color code is right, but the subscript is wrong. Okay, and now the reason is because this is a quadratic form, right? And if you plug in something that is antisymmetric, because if you move to the other side, you get a negative sign, so it cancels with itself. Okay, so the only thing left is the symmetric contribution, and you can do some interpretation of parts, and you realize that in this setup, the only thing that contributes to this Dirichlet form is the derivative in the v direction. And for sure, because this observable is both a function of variable x and v, if you only take in derivative in the v direction, it's impossible that you can control the L2 norm, right? Because you can just take any function that only depends on x, you plug in, and then this is 0. This is something non-trivial. All right. So which, in other words, it means that if you relies on coercivity or relies on trying to get the spectral gap, it will never work. Okay. So, due to this reason, if you want to establish kind of quantitative estimate for these non-reversible dynamics, you need to use something a little bit more sophisticated. And in the field, this is known as the hypocoercivity. Okay, so that is a weaker notion of the coercivity. And I won't go into the history of establishing the quantitative bounds, but just mention that even in the classical literature, in the PD context, these techniques are also recent. Okay. All right, so now, let me just summarize what we can say about this classical case. And before this is also serve as a motivation of what we are trying to do in the quantum case. Okay, so now what is hypocoercivity? Why we need this hypocoercivity, or what does it really mean? Okay, so now recall that, there's the reason for doing these hypocoercivity, or these things appears, is, you can understand it as the coercivity fails, but you can also understand it as if you have two parts of the generator, and the damping part you rely on, the symmetric part, which is the damping, the kernel of that damping part is actually non-trivial. Okay, so dimensionality of that is greater than 1. Okay, in other words, if you just drop the coherent part, if you drop the Hamiltonian part, if you just drive the Lindblad using damping, it will not converge to a unique stationary state, because the kernel has dimension larger than 1. So in this particular, the Lindblad case, you can characterize the kernel as this, okay? So that anything that is commuting with the jump operators and is, adjoint, would lie in the kernel. And also in the classical case, it's more easy to characterize because everything that only depends on position would be in the kernel, okay? So now, in other words, if you just think about damping, okay, so that it would not work, so that because the kernel is non-trivial, you need to combine the effect with the antisymmetric part of the generator, okay, to drive you to the unique equilibrium. Okay. So this is, of course, a qualitative picture. So that you need to consider the interaction of both of the Hamiltonian part of the dynamics and the dissipation, and the so-called hypocoercivity estimates are trying to make this more quantitative. Okay. And now, in the classical case, before I go to the quantum or more general cases, in the classical case, one can establish such a theorem. Okay, so remember that the overdamped dynamics converges is the Poincare constant as the rate. Okay, so m. And what you can show is that for this underdamped dynamics or for Langevin dynamics, where you lifted the process to a larger state space, okay, and you characterize the same convergence, also in L2 in the weighted measure. Okay, and what you can get is such a the explicit estimate with some constant here, so order one explicit constant times e to the minus lambda t. And what's important is that you can have a very explicit characterization of the convergence rate, lambda, which is given here. And again, C0 is some universal constant, and m is the Poincare constant that you assume for the invariant measure, and gamma is this damping parameter. Okay, and it tells you that actually how large a damping you need to choose. Okay, so in particular, the damping parameter here is the square root of m. And remember that, we're interested in the case of accelerating the process, so that typically the m is kind of small. So that's the original chain has slow mixing, which means that it's better to operate in a regime where the damping parameter is actually fairly small. It's far from the overdamped limit, even though we're using that to kind of derive the collapse dynamics, and we think about this as a lifting relation. Okay, but in order to achieve this optimal convergence or optimal convergence rate, we're kind of operating far from the overdamped limit regime. Okay, and also in particular that if you choose this gamma to be square root of m, and if you calculate, and the convergence rate is square root of m, so there was a quadratic acceleration. Okay, so now just to put this kind of in the context, so let's also for simplicity of notation, let's just always assume that average is equal to 0, so that we don't need to carry this average around. All right, so what we get is such a estimate. Okay, so there was some constant times e to the minus some constant, absolute constant times the rate. Okay, and the rate is square root. Okay, so let me make some remark about this result. Okay, so first of all, you observe that this, this root m, this is very similar to the lifting of the discrete case. So we have a diffusive to ballistic acceleration. Okay, and in particular, it's ballistic acceleration because if the damping, if you think about dynamics, okay, so dynamics is where? Okay, so if you think about dynamics, if the damping is really small, then this part is non-reversible, so that you're just following a deterministic Hamiltonian flow, right? So that's why it's kind of transport behavior instead of diffusive behavior. Okay, and also in this case, if you just fix a Langevin dynamics, okay, as your lifted process, and you can easily calculate using explicit example. So imagine, for example, if you take U to be a quadratic potential, and you can check that this square root of m convergence is optimal. Okay, you cannot do better. It's not a caveat of analysis, and the square root is m is sharp. Okay, of course, this remains the question open that whether you can design some other processes that goes, kind of adding some actual variables to the overdamped dynamics and maybe accelerate faster. So that we haven't answered that yet, but just mentioning that if you particularly fix the dynamics, this is the optimal that you can achieve. And also you may notice there is a constant here which actually does not appear for the overdamped dynamics and because of a spectral gap. So let me just mention that this is indeed a feature of hypocoercivity, so that there must be a constant here, because if there is no this constant, you can actually assume, you can actually prove when taking t to 0 that there is a spectral gap. So there is going to be coercivity. M is a Poincare constant. Okay. So I'm not going to the proof of the PD proof, but the proof relies on an extended version of the Poincare inequality. So the usual Poincare doesn't work because the usual Poincare is just the spectral gap. So we need to do a so-called space-time Poincare inequality and to handle the lack of coercivity. All right. So let me, I already mentioned that. If you just look at this result, it's actually kind of the door is still open. So maybe you think, actually, if you think about classical continuous sampling, there was recently in recent decade, there was a huge amount of activity in designing different samplers based on some different continuous Markov processes, such as HMC, so PDMP, piecewise deterministic Markov process, event-driven chains, and so on and so forth. So so maybe there was still hope to think about accelerating them further. Okay, but this is a question that whether you can beat this diffusive to ballistic acceleration barrier. Okay, and of course, for this workshop, we are probably more interested in quantum cases, right? So that now, so if we think about the following question, right? So that if you think about the overdamped dynamics as the chain that we're kind of interested in sampling, okay? Or in other words, here, in the quantum context, you have a detailed balanced Lindbladian dynamics, okay? That you write down, so that so it's a detailed balanced quantum Markov process, and now. The question is that whether you can find a non-reversible dynamics, okay, so that which is a lifting, okay, of the original Lindbladian dynamics. You extend the state space to achieve maybe a quadratic speedup, okay, acceleration. It would be nice to achieve things better, of course, but at least whether you can achieve something, okay. So this is the motivating question. All right. Any questions? Oh, it's a good time to, because I finished the classical story before jumping to more quantum stories.
Why lifting?
Because otherwise the analysis is more harder, so it's ongoing work. So if you, you can do it, yeah. But all these previous examples in the discrete world or in the classical world, you see that the collapsed chain or the bottom chain is detail balanced. Okay, so that's why we are starting from here. Okay, and also many of the Lindbladian dynamics people use in practice are detail balanced. Okay, so now for doing that, first of all, let's give a more precise definition of what lifting is. Okay, so far it's very, very kind of hand waving. Okay, so on and so forth. So this is the reason that we actually can think of this as an opposite of the overdamped limit. So let's just recall what is happening in the overdamped limit, right? So the idea, the goal is that you have this quantum semi-group, okay, which is given by gamma, and you're thinking about this gamma goes to infinity limit, and you want to characterize the dynamics using effective generator, okay? And the structure, the usual structural assumption here is that the L gamma is given by the antisymmetric part, and this should be symmetric part, okay? And with the damping parameter goes to infinity, and in particular because of this structure, so the invariant measure or the stationary state of this Markov semi-group actually does not depend on gamma. Okay, so that they fix the sigma, so that for any gamma they have the same invariant measure. Okay, so that's so we can actually just vary gamma without changing the stationary state. Okay, so now the first observation already we have seen is that in order to take the overdamped limit and to get something non-trivial, okay, because the effective dynamics was acting only on the kernel of the symmetrical part of the generator. If you want something non-trivial dynamics of the collapsed chain, it's better to assume that, of course, the kernel is non-trivial. Okay, otherwise you get nothing. Okay, so this is actually also, as I pointed out before, that this is the feature of these Langevin and Lindblad dynamics when you work in this hypocoercivity regime. So that this is the hypocoercivity assumption. Okay, now the second thing is that when we do this asymptotic expansion and to match out the asymptotics, you observe that if this is not zero, okay, so if the recall that this is the projection to the kernel of the symmetrical part. Sorry, this is the typo carries along, and this is the antisymmetrical part of generator. And if that's not trivial, that's not zero, then you get actually the first order dynamics, which is given by that without even time rescaling. And this, you can think of this as that in the LO, okay, so it's the effective generator. Now, in this case, we can call this the L gamma, this lifted generator on the extended space, as a first order lift. Okay? And this is, in fact, if you carry out the same calculation in the discrete case, okay, discrete time case, this actually corresponds to this lifted Markov chain that was constructed by Percy Diaconis and collaborators. Okay, so it's in the first order case. Now, and as I have already mentioned, and which is also, you can verify simply, for these particular examples. So for Langevin and for some Lindblad dynamics, so actually what we have is that this first order, the generator actually vanishes. Okay, so, and now, for that, we need to go to next order. Okay, so looking at longer time scale. Okay, and then what we get is a more complicated effective generator type, which is of this kind. Okay, so which is kind of connection with the original generator of the lifted chain, lifted process. Okay, and then because of this, we are going to the next order, so that this is called in the literature the second order lift. Okay. So this gives you, this gives you a picture that when we have, so remember that our kind of goal was reverse engineering to some extent, right? We have a, detail balance generator, and then we want to kind of lift it up. Okay, but this at least tells you that if you have a lifted up chain, if you lift a process of this structure, then what will be the collapsed chain? Okay, so now coming to the definition. Okay, so and in the classical world, this concept of lifting was first the continuous process was first done by Abele and Lawler, 2024, and we're trying to give this a more unified picture and also extend it to quantum case. So now if you think about these two generators, okay, so that this is the generator of the non-reversible case, and this is the effective generator. We are considering the second order case, okay, which seems to be more relevant for Lindblad and Langevin. Okay, so we have actually essentially two conditions for this lifting relation. Okay, so that one is the condition is that so the kernel of this symmetrical part is greater than 0, or in other words, if you think about in terms of damping or noise, it means that this noise or damping is degenerate. Okay, it does not acting on the whole degree of freedom. And one physical example could be that if you have a chain and your thermal bath is only acting on the end of the chain. Okay, so there is nothing in the bulk. Okay, so this would be a typical example of the case where the dissipation in the kernel would be greater. Is non-trivial. Okay, and now we can also do first order lifting, but as I said, we'll focus on second order lifting in this talk, and so because of that, we assume that this first order is vanishing. Okay, so there is non-trivial. This is also refers back to the talk maybe by Professor Collins saying that if you both of effects appears, first order and the second order, then the analysis becomes less more tricky. But so we simplify the story, so that's just saying that the first order is 0, so that we just focus on next order effects. Okay, and now, in the classical world, this is all in a way. Okay, in the quantum world, there was this thing called complete positivity, so that which is quite non-trivial. I think was also appeared in Anthony's talk. So you can do this thing. You can calculate the effective generator, and you can look at the semi-group. And this semi-group is, it's not so hard to check that this semi-group is actually going to be symmetric, as you can see from this form of the generator. Okay, and you can also check that it's going to be contractive with some unique fixed point under some reasonable assumptions. But in general, it's not very trivial, very easy to check that it's completely positive. Okay, so now if you really want to view this as a lifting, so that if you, so remember that in lifting you are going to opposite direction, right? It's kind of the reverse engineering. You're starting with a QMS and you want to do lifting. And if you really want to do that, then of course we need to make assumption that this is indeed a QMS. Okay, or in other words, this is a Lindblad operator. Okay. But now, if this is your goal, right? If you want to design lifting, then of course it's natural to start with a QMS, and then you're thinking about how to do lifting. And now, in the other direction, if your goal is to understand the convergence rate of this generator, okay, with respect to gamma, some choice of gamma, then it's actually okay that you do not assume that this limiting process is completely positive. And in that case, we can just drop that condition. Okay, if you're interested just in understanding convergence rate. Okay, but to be a faithful lifting, then this is the definition. So if these conditions satisfy, then these generators satisfy these relations. Is that clear? Okay. And another way to understand the second order is that you see that there is these kind of things appears. Okay, in the first order lifting is much easier, just pi s, LA pi s. Okay, so this is the framework, and with the last minutes, let me just tell you what we can have. So now we assume that the collapsed chain is detail balanced. Okay, so that if there was a gap, then of course you expect exponential convergence. And we want to understand, how about this the lifted process, right? This, the hypocoercive process, and also recall that because it's hypocoercive, so that this is kind of thing we expect. So there is some constant, absolute constant, and with some rate, okay, which may depend on gamma. Okay, so for simplicity of notations, I always assume that the average of these observables is equal to 0, so that I don't need to put them in these equations. And I always work in Heisenberg picture. Okay, so I'm only looking at observables. Okay, so now our results, informally speaking, is that we can establish two things. So that, first of all, we can establish the upper bound, which in a sense tells you that how much acceleration you can get. Okay, and also, but upper bound essentially tells you that you cannot do better than quadratic acceleration. Okay, and now the perhaps more interesting result is that we can also get explicit estimate of this non-reversible Lindbladians. Okay, so we can establish lower bound of the convergence rate. Okay, and then so that if you want to achieve acceleration, then perhaps it's better to lower bound matches upper bound, and so that you can get accelerations. Okay, so let me just give you these results in slightly more detail. So first of all, this is so this upper and lower could be confusing because which direction of the inequality you are taking. But by what upper bound, what we mean is just that this is the best possible rate you can possibly get. Okay, and then the result is that the answering, I guess, Lin's question is that if you work in the lifting setup, the best possible thing to achieve is the quadratic speedup. Okay, so this, does not have nothing to do with complexity theory. This is really just analysis, it's PD analysis. Okay, so the best possible rate is the square root of gap. All right, and now the understanding of this, the heuristic understanding of the result is actually quite easy. But then you need to do some setup. How to characterize the convergence rate of some process that is not detail balanced. So instead of the spectral gap, you can talk about singular value gap, and so on and so forth. But maybe let me just give you, instead of going to the proof, let me just give you intuition, because you see that, there is a connection between the overdamped dynamic generator with the lifted generator, and there's appear twice the LA. So vaguely speaking, what you do here is kind of like taking a square root. Okay, so that this generator of the lifted process is kind of like a square root of the original process. So which means that if you originally have a spectral gap, then if you consider singular value gap of the lifted generator, there is a square root relation. So that's why it's this quadratic relation. Okay, you cannot do better than that. Okay, and okay, of course you can imagine if one can do higher order lifting, but you cannot be this either. So that we can go, these things in offline. Okay, but I guess more interesting is that this is kind of a negative result in the sense that the best you can achieve is like a quadratic speedup. Okay, so now okay, well, how about on the more positive side? Okay, so what are the kind of best possible acceleration? Okay, so now this is the lower bound we can prove. So this is kind of the main result because this is analysis of non-detail balanced generators, which is far from easy. Okay, and now we can get the explicit characterization of the hypocoercivity rate. Okay, with this new t, and t is a parameter one can tune, and also same as gamma. So I will mention what t is later. So we have explicit characterization given by this. These are some constants which are explicit, but the expression is long, so I don't want to write them down. Okay, and given by this, of course, it suggests that you can maximize. You want to enlarge this convergence rate as much as possible, right? So you want to maximize this relation, and it's achieved as this constant. Okay, and also you choose the t. Going to here. As related with the square root of the gap of the reversible generator. Okay, and in particular, if you plug in these choice of parameter, what you have is that you can work at this particular damping rate, gamma max, and you achieve an explicit convergence rate of this type. Okay, so you see that there is a square root of gap. Okay, but it's not simple as that because there was something else that comes in the denominator, and where there's some additional constant that you want to clarify. Calculate, and these constants kind of can try to bound essentially the generator of the collapse dynamics in terms of, in this way, right? So that they are kind of related with the collapse generator. Okay, all right. So, sorry. It's a case-by-case calculation. So that you need to kind of go into examples. So I think my time is running up. But let me just briefly mention that the proof is based on the so-called flow Poincare inequality, or which is a special version of the space-time Poincare inequality. I don't think I have any time to go into this. So maybe for the last minute, let me just mention the following. So how to achieve the optimal lift. So we have seen that there was upper bound, so the square root of gap. So we want to find examples so that, we can achieve optimal bound so that this constant here is order 1. Okay? And now, because I have run out of time, so that you can refer to paper, there are some examples that we can calculate this. And for example, if you're starting with a Markov chain, and so on and so forth, But maybe the one thing that last minute that I want to connect with Professor Collins' talk, and in fact, for this bipartite system lifting, okay, so that if you think about HA and HB, you have some coupling, okay? And in that case, actually, we can explicitly construct lifts, okay? And we can work, so let me just quickly go through this so that we can do that. So there exists a lifted chain for any of these bipartite kind of constructions so that you have original chain, you kind of put in auxiliary systems, okay, into a tensor product. And to achieve optimal lifting, the key assumption or the key construction here is that the original chain needs to satisfy so-called kappa intertwining condition, okay? So which was actually first written down by Professor Collins in the earlier paper, okay? And in that case, we can achieve acceleration, quadratic acceleration, okay? So let me just end the talk with maybe just this result and just mention some examples that, was calculated over the years by some of the participants of the workshop, actually, so that, Ligo, I think, is sitting behind there, and maybe here. And then, you can, if you want to know what these things are, you can talk to me offline or maybe talk to Lee afterwards, okay? And with that, I want to conclude my talk. So there were a lot of open questions about this lifting. So, so in some sense, we developed a framework of analyzing this convergence rate of the non-reversible dynamics. But it's also, by the way, it's also true in Castle case, so that how to construct good lifts if you're given a chain. Okay, so this is relatively quite open in the quantum case, so we can have some construction of the kappa intertwining conditions. But what about the general cases? How to go beyond these things? And now, as was mentioned during the talk, how about non-reversible? If you start with an NESS, how to do lifts? So these are all interesting questions to investigate. Okay, with that, I want to thank you for your attention and happy to answer any questions.